To find the electric field intensity due to a uniformly charged conducting sphere. The conducting sphere, and it has a volume V, that is equal to 4 by 3 pi r cube. It has a charge Q which is distributed uniformly over it. Because it is a conducting sphere, that means for conducting sphere, we have already mentioned that charge in electrostatic state will reside at the surface of conductor. That means if charge Q is given, say charge Q is the positive charge, if this positive charge is given to the sphere, which is a conducting sphere, at static condition, this charge will be at the outer surface of the conducting sphere, and there will be no charge inside the surface. So now the situation is like the spherical shell. On spherical shell also, charge resides at the surface, and we found that for spherical shell, electric field ER was 1 by 4 pi epsilon naught Q by R square for R greater than capital R. It was equal to 1 by 4 pi epsilon naught Q by R square for R equal to R, and it was 0 for R less than capital R, and also 0 for R equal to 0, that is center. Same are applicable for the conducting sphere, and same can be derived using the Gauss law. If we use Gauss law states that flux integral E dot ds equal to charge enclosed by epsilon naught. This is the Gauss law. Now we apply this Gauss law for an external point P, which is at a distance r from the center O. For this point P, we take a Gaussian surface, which is also a spherical surface, and passes through point P, and this Gaussian surface is represented by a dotted line. On this P, we take an elementary surface area, this is ds, which is outward always and normal to the surface, and E is also radial, and it is parallel to the surface area. If we take another surface area on the Gaussian surface, the field surface area is ds outward and perpendicular to the surface, and electric field is radial, because distribution of mass is symmetric for all points on the Gaussian surface. So E is also outward, radial, and parallel to ds. That means angle between E and ds is always 0 degree for this Gaussian surface. Therefore, for r greater than capital R, that is the point external to the sphere, integral E ds cos 0 equal to charge encloses, it encloses whole sphere, so charge encloses the charge on the sphere, that is Q by epsilon naught. E each constant in magnitude is taken out, integral ds, and cos 0 is 1. It is equal to Q by epsilon naught. And integral ds for a spherical surface is 4 pi r square. R is the radius of the Gaussian surface, and Q by epsilon naught. Therefore, E equal to 1 by 4 pi epsilon naught Q by R square. It is same as we have derived for the spherical conducting shell. Similarly, for R equal to capital R, we can simply put small r as capital R, and electrical intensity will be 1 by 4 pi epsilon naught Q by R square. For R less than capital R, that means point is lying inside the spherical shell, and in static state, charge resides at the outer surface of the spherical shell. There will be no charge inside. That means field inside is 0. Same can be derived here as if point P is inside the sphere surface at a distance r, this is the point P, we draw a Gaussian surface of radius r, this is spherical surface, and apply the Gaussian law integral E dot ds equal to cube inside or enclosed by epsilon naught, this is the Gauss law. And now we apply here again, this surface area ds is outward perpendicular to the surface and E is radial parallel to the ds. So angle between them is 0 degree. So we can write integral E ds cos 0 equal to, and charge enclosed by the Gaussian surface is 0. Why 0? Because total charge resides at the outer surface and Gaussian surface is inside the outer surface. Therefore, there will be no charge inside the Gaussian surface. Hence, charge enclosed is 0 divided by epsilon naught. So, this implies that integral E ds equal to 0. And because ds is the elementary surface area on the Gaussian surface, so integral ds for the whole enclosed surface will be 4 pi r square. That is, it is not a zero quantity. This implies that electric field will be 0 at a point inside the conducting sphere. On the same way, for r equal to 0, that is at the center, because all point inside the field is 0, so at the center will also the field will be 0. And we can draw the graph for E and R, and it will be similar to the spherical shell. This is R, this y-axis we take an ER, and drawing the graph, we take the point R equal to 0 as the center, and it is taken at origin, and this point is showing the radius R equal to capital R, and at R equal to capital R, electric field is 1 by 4 pi epsilon naught q by r square. This is the maximum electric field, because after that distance increases, and as r increases, electric field intensity decreases, because there is an inverse relation. Hence we can draw the graph that for r equal to 0 to r equal to capital R, the field is 0, then it becomes maximum, and after that it decreases, and it decreases on the rate as E proportional to 1 by r square, and for r less than capital R, it is E equal to 0. So this is the ER graph.